operator commutes with a Hamiltonian. I haven't actually proved that if operators commute, they have a simultaneously diagonalizable set of eigenstates, right? But we have seen evidence against it, to the contrary over here, right? Like if they don't commute, then you can't have them have a simultaneous eigenstate. It violates the generalized uncertainty principle. But it is in fact true that if they commute, you can find a simultaneous set of eigenstates for them. In other words, a basis for the set of state vectors for which it's both a set of eigenstates for the first operator and also the second. So this Hamiltonian, right?
Wait, can you repeat that? You said if they don't commute, uncertainty principle is what violates.
If they don't commute, then that makes this non-zero,
Mm-hmm.
which makes this non-zero,
Mm-hmm.
which means that neither of these can be zero,
Mm-hmm.
which means I can't know either uniquely.
Okay.
Yeah.
But if they do commute, this is the case.
Yeah, if they do commute, essentially by definition, the uncertainty. Well, excuse me. If it's an eigenstate of an operator, then the uncertainty is zero. So that. Now over here, if we have an observable, right, which has no time dependence, this is zero, right? And if that observable also commutes with a Hamiltonian operator, that says that the time derivative of their expectation value is zero. In other words, they're constant in time. Right? So, to give you a somewhat esoteric example, you can look at something like, goodness gracious. I don't know, later when you study more complicated things, you start angular momentum and things, you'll learn that like the square of the z component of the angular momentum will commute with certain Hamiltonians, whereas, I think the square of the z component will commute, or the z component will commute, but the x and y won't. So like you can use the z angular momentum as an eigenstate of definite energy. See, that's the thing, is if you have an eigenstate of q, right, whatever the energy is of that state, it doesn't change. That's another part of this. So now let's see here, Ehrenfest's theorem was what? It was that the expectation of the momentum, right? So let's see here. I think if I apply this to say q hat equal to, let's say, momentum maybe? What happens if I, maybe just the momentum, maybe just the Hamiltonian itself, right? So the Hamiltonian itself is p hat squared over 2m plus the potential, right? So does h commute with h? Yes. All right, so that's zero. And so you get, and then what's the, stink. It's not quite right. Well, what does that say then? I got partial, I should get, I'm not sure, it's interesting. The partial, this partial t, right, is equal to d dt of the expectation value of h, right? Oh, this is zero as well. I'm sorry. Yay, okay, so, yeah. The energy is constant. Great, yeah. This just tells me that the expectation value of the Hamiltonian is constant, which is good because that's the energy. So if you have h psi equals to e psi, then that's the energy is the energy is actually the eigenvalue of the Hamiltonian. I have a sense that Ehrenfest's theorem is in this stupid thing. But anyway, I enjoy this calculation. Sorry. We probably, of course, should get back to further explicit examples. Well, sort of explicit examples. So next time, I will try to work out the harmonic oscillator for you guys, the quantum harmonic oscillator. Let me show you what that looks like for a second. Let's just look at the raw mathematics of it, if you guys don't mind. Do you have a minute or two?
Mm-hmm.
Okay. So the criticism that I've read of Griffith's books, more or less, it's sort of too elementary. Maybe, I don't know if that's entirely fair. It's not. I mean, there are more complicated quantum mechanics books for sure. But another sort of common criticism is it overemphasizes wave mechanics, and so wave mechanics is. What I've been doing today for the most part really isn't wave mechanics. I've been emphasizing to you the Brockett formalism, which is, I think, more accurately how it's practiced. But the sort of the wave mechanics version of things, I think it's a little bit easier to conceptualize. There is some sort of conceptual something to grab onto there. But what I've observed is that when you actually hear practicing physicists do things with quantum mechanics, they're not really doing wave mechanics. They're doing it's more like Brockett formalism sort of stuff. I don't know. That's just whatever. But so what is the classical, we have F equals to minus kx, right? That's Hooke's law. But if that's equal to minus dV dx, where V is the potential, what's the potential? V is equal to 1/2 kx squared, right? So, what's the Schrodinger's equation we want to solve? H bar squared over 2m, right? Partial squared psi, partial x squared, right? Did I get it right? I keep forgetting that stupid thing. It's a good thing I don't teach quantum mechanics. Alright, let's see here. Well, barely. Let's see here. Where'd that stupid thing go to? Sorry. Yeah, there's a kind of important minus I'm missing right here. Yeah, okay. Minus h bar squared over 2m plus, so then plus 1/2 kx squared, right, equals to I h bar partial psi partial t. Alright. And, of course, psi is supposed to multiply this thing here too. I think we can separate variables, right? We can say like f times psi, like he does. And then, what's this give us? I guess this is all supposed to be over psi, right? It's all over f, and that's equal to e, right? That was our separation of variables. So, for the time, we get something like f of t is equal to something like e to the I haven't done this wrong. Minus I t over h bar. Oh, there's an e though, right? Sorry, let me spell this. So this, I got df dt. Sorry, I'm just dead. Let me do the math here. Df dt equals to what? It's equal to e over h bar I, right? Or let's say minus I over h bar, minus IE over h bar, right? That's df dt times f. So f is equal to exponential of minus I e t over h bar. Great, that's the time thing. And then over here, we're trying to solve what? We're trying to solve h bar squared over 2m, right? Psi prime prime, plus 1/2 kx squared minus e psi equal to 0. And then, ostensibly, we've got maybe some sort of reasonable, like the question then is like, what kind of boundary conditions are we looking at? You know, this is the quantum harmonic oscillator, right? Let's see what he has to say. Oh, use a slightly different notation. Stink. Shrink. So he's got minus h bar squared over 2m, 1/2. Instead of writing what? There's a sneaky step in here I didn't notice. He rewrites, instead of writing k, he rewrites the k as like say let's, this is, of course, this is going to be equal to m, ma. So the omega square root of k over m. All right, so instead of k here, we put, for reasons of tradition, if nothing else, 1/2. Stink. That's, goodness gracious. Forgotten all my traditions. I am so sorry. That's m omega squared. I guess that makes sense, right? This says that k over m equals omega squared, so k is equal to m omega squared. Okay, fine. It's just, anyway, it's just, in some sense, just nomenclature, right? M over 2 omega squared x squared, but it's important that we get on the same starting point, all right? Now, how do you solve that?
It looks like a linear constant coefficient.
He says, what he says but that x is not constant. Those are derivatives with respect to x, so psi prime is like t psi dx.
I thought they were on t.
Here's what he says. He says, in the literature you'll find two entirely different approaches to this problem. The one is a straightforward brute force solution to solving the differential equation. This involves power series expansions and things called Hermite polynomials. All right.
My least favorite part of ODEs.
Those were not fun.
And
It
then
just didn't seem practical.
the other way to do it, and this is important because it also plays into a larger story. And if you go on to study quantum field theory, these ladder operators play a significant role. The other way to do it is use a ladder operator technique. I'd really like to look at both in here with you guys, honestly. But what I'm trying to fish through here is like, okay, so that's the differential equation, right? What are reasonable physical assumptions on the wave function then? Like, what's the boundary conditions we should expect here? I understand for a heat equation, for a wave equation, these boundary conditions I have an understanding of. Even for the infinite square well we talked about the other day, it makes sense to me. Like phi of 0 has to be phi of L, right? Made sense. What if anything are the boundary conditions here?
Phi double prime equal to 0 at both boundaries.
I don't know.
Well, at least phi. I feel like phi prime
I think.
equals 0 at the boundaries, right?
Yeah, I think. I don't think there is any assumption that. X can go on and on, so it's not. Basically, if you think about a spring, right? Is it bounded between two particular? If there's more energy, it just springs further and further, right?
Mm-hmm.
At least in principle. In practice, of course, spring breaks, right?
Yeah.
So I guess we're not looking at that. It's sort of an unbounded problem in that regard.
So asking us the values at the boundaries are a trick question.
What was the question I asked with honest intent, but it's a trick question, yeah. From what I'm seeing and remembering. So, but what we're going to find though is that while we'll find that the energy is quantized in this problem. It takes on a certain discrete. It jumps from one thing to the next to the next. The tiny jumps. It's a very misused phrase, like a quantum jump. Like it's a quantum leap. It's like, well, that would be like a really, really small leap. But this is a popular missaying, so I can't discredit the people who use it. I understand why they use it. It's just not physically accurate. Whatever. Anyway, and then his next section in here is on the free particle. Basically, in the free particle section, it goes back to that stuff I was telling you guys about, where he finds a solution. He finds the free particle solution pretty easy, but then it's not normalizable. So, like, what does that mean? It means that you have to look for like a wave packet, and then like, how is that? Anyway, I'll read you some more. Or maybe we can read along together if the books come. But anyway, so next time, we'll hopefully figure out how to solve that, at least using the ladder operators. It is a beautiful piece of abstract linear algebra, really. Really neat eigenvector commutator stuff. Yeah. Anyway, if nothing else, I hope you've left today with an understanding that commutators matter to quantum mechanics, and this is why.
Still got a lot of digesting to do, but it's starting to slowly make
Yeah,
more sense, I think.
don't get indigestion.
Don't get into what?